Hello, students. We reached chapter 7. The topic is activity and the systematic treatment of equilibrium. In this chapter, you will learn what is the activity is and how you calculate the very complex chemical reactions using mass balance and charge balance. So this chapter is the basis of the calculations appeared in all kinds of chemistry. Okay, let's start. First, you have to be aware of hydration. In most cases, we are working in aqueous solutions, which means the solvent is water. Okay, in water, the behavior of species, which is molecules or ions, are different from when they are in air or in the solid state. Okay, because waters in many cases surround the ions. Okay, let's take a look at this figure. As you know, water is a dipole molecule. Okay, it has dipole moment, very large dipole moment, because water, the molecular structure is bent. It has a bent structure. Okay, the angle between hydrogen, oxygen, and hydrogen atom is not 180 degree. It is about 104.5 degree. So it's bent. As you know, every atom has electronegativity, which measures how strongly the nucleus of an atom attracts electrons toward itself. Okay, so the famous chemist Linus Pauling measured the electronegativity for every element in the periodic table. The the element having highest electronegativity is fluorine, then oxygen, then nitrogen, etc. Okay, so the oxygen has very high electronegativity. It uh, draws the electron cloud toward itself, so it takes partial negative charge. The hydrogen atom, its electronegativity is smaller than oxygen, so the electron cloud around the hydrogen atom is drawn toward oxygen. As a result, the hydrogen atom takes partial positive charge. Okay, although the total charge is zero, it's a neutral, but actually the charge separation occurs within the water molecule. As a result, water molecule becomes dipole, right? Which the dipole plays a very important role in uh, when it reacts with other species. For example, when you dissolve lithium chloride in water, they completely dissociate, okay, leaving lithium positive ion and chloride negative ion. Okay, and this lithium ion is hydrated because lithium ion takes a positive charge. As a result, there is an electrostatic attraction between the water oxygen atom, because it takes a partial negative charge and lithium takes a positive charge. So there is an electrostatic attraction. In the same manner, the chloride ion now uh, attracts this hydrogen atom, because the hydrogen atom here takes partial positive charge. Okay, there is also the electrostatic attraction between this chloride ion and hydrogen atom in water. Okay, so here this is summary. Ions and molecules in solution are surrounded by an organized sheath of solvent molecules. Sheath means layer. Okay, this kind of solvation is not unique for water. If you use other solvents like acetic acid, you expect the same kind of the solvation. Okay, the important is that in water, those ions don't behave alone. They always takes water molecules around them. Okay, and lithium ion actually have has 4 water molecules in the first coordination sphere. In the meantime, chloride ion has 6 water molecules. Okay, in the first coordination sphere, which means this molecule, and there is another molecule, water molecule, and there are 4 which constitute the first coordination sphere, and beyond it there is another coordination sphere of water. Okay, but the first coordination sphere, the water's molecules are very strongly attracted to lithium ion. Okay, but keep in mind that this one, water molecule exchanges rapidly between bulk solvent and ion coordination sites. Okay, but this water molecule is exchanges rapidly. Okay, with the water molecules in the bulk. All right. So this table shows you um, how many water molecules are tightly bound to each species. This one, the first one, this is propane. Yeah? It doesn't have dipole moment. Okay, so it is not bound to water. Okay, and benzene also. Yeah? Benzene is has no dipole moment, so there is no tightly bound water molecules around propane or benzene. But as uh, the high the electronegativity atoms are attached to these molecules, and then water, at least 1 or 2 or 3 water molecules are bound around this species. For example, this one. What is this species? Yeah, this is ether. Okay, dimethyl ether. Oh no, I'm sorry. Yeah, this is that. This is not. Let's see. This is ketone, right? Um, aldehyde, acetaldehyde, right? This water oxygen atom is there. So, although this part is not polar, but water, yeah? Since water atom, the oxygen atom is attached, then electron density is drawn to the oxygen atom, right? So, as a result, uh, there is 1.5 water molecules on average. Okay, like that. This is acetic acid. This is more polar than this one, acetaldehyde, right? So there are 2 water molecules like that. And here is an extreme case, which is the ammonium ion. Ammonium ion, one ammonium ion now takes 12 water molecules. Okay. So the important is that in aqueous solution, many species have water molecules around it. Okay, so we have to consider the hydrated ion size. In general chemistry, you've already learned that um, the size of the the elements, in the periodic table. Okay, and lithium size is very small. Of course, the smallest one is what? The hydrogen atom. Okay, anyway, lithium ion is very small, but when it is in aqueous solution, then there are at least 4 water molecules around this lithium ion. So hydrated lithium ion size is not that small. okay, is actually it is bigger than maybe sodium ion or potassium ion. Okay, the ion itself, sodium ion is bigger than lithium ion, but hydrated radius is different. Okay, yeah, like that. You can, visually, you can appreciate the size of hydrated ions, right? So this hydrated ion size plays an important role in um, ionic in activity. Okay, you will see soon. Okay? But how do we measure this size of hydrated ions? There is a technique called X-ray diffraction. Okay, ionic radii are measured by X-ray diffraction of ions in crystals. Okay, so you make a crystal, and then you use X-ray diffraction. All right, yeah. But how do you measure the hydrated radii? Yeah, they are estimated from diffusion coefficients of ions in solution and from the mobilities of aqueous ions in an electric field. Okay, using these techniques, yeah, we can roughly, roughly, not exactly, estimate the hydrated ion size. All right, yeah, okay, and the diffusion coefficient in solution, or in solid state, or even in a gas state, right? The species diffuse out because to make the concentration even, right? And let's see, this lithium ion, since it is small, okay, so diffusion is rapid for lithium ion. But since it is hydrated, the hydrated size is bigger than the lithium ion itself. Yeah? So since size becomes bigger, the diffusion becomes slower. Okay, and also the mobility here you will see, yeah, soon. Mobility also becomes slower. Yeah? Mobility is the ion velocity, yeah, divided by electric field. Okay, smaller, more highly charged ions bind more water and behave as a larger species. Okay, as I said, this one, although this lithium ion size is small, but hydrated ion size is bigger than sodium ion or potassium ion or even rubidium, maybe a rubidium ion, maybe similar. Why? Because the size is small, right? Ion size is small, and then more tightly the water molecules are bound. All right, and this one highly charged one. Let's look at this one. This beryllium ion has two positive charges. Okay, and these water molecules are more tightly bound around this beryllium ion. Okay, the same argument applies to the anion case. Okay. Yeah, here is a demonstration of this ionic atmosphere. Okay, you see the ferric ion takes the pale yellow color, yeah? Not very strong, but very weak yellow color. But this ion, cyanide ion, it is colorless. Okay, but when they make a complex, this one, it takes very strong red color. Look at that. These two because the solution is the same. This one, ferric thiocyanate, the solution is there, and uh, into this beaker you add potassium nitrate, and suddenly the color changes to yellow. Okay, so in this case you can think, oh, the equilibrium moves toward left, toward the rectant side. Okay, because the color changes yellow. Okay, but this potassium nitrate, there is no potassium nitrate. It is completely dissociates, leaving potassium ion and nitrate ion. But in this reaction, there is no potassium ions nor the nitrate ions. Okay, and the equilibrium constant by definition can be written by this equation. Okay, here no potassium, no nitrate ion concentration appear here. So from principle of equilibrium constant, you may say that no matter how much potassium nitrate ions are added, the equilibrium constant remain constant. Okay, really constant. But actually, this equilibrium constant K value decreases as potassium nitrate, the amount increases. Okay, here K decreases as potassium nitrate is added, but there is no common ions. Okay, you know that common ion effect, right? If you add thiocyanate ion and then from the common ion effect, the equilibrium becomes to shift toward the left side. But still, in that case, okay, still in that case, this equilibrium constant remains the same. Okay, I'm sorry. If you add this common ion and then the equilibrium shifts toward the right side here, yeah, to decrease this common ion. Okay, but in this case, there are no common ions. Okay, so common ion effect doesn't apply. So the question is why? Why the color changes? Okay, and this figure uh, is the demonstration of equilibrium constant versus potassium ion concentrations. So as you add more and more this potassium ion, potassium nitrate to this compound, and then equilibrium constant becomes smaller and smaller. Okay, the question is why. Okay, let's consider the effect of ion strength on solubility of salts. Okay, yeah, let's consider this one, the solubility of calcium sulfate. Calcium sulfate is not very soluble in water, is sparingly soluble. The Ksp of this compound is 2.4 times 10 to minus 5, the small value. So someone measured the solubility of calcium sulfate and he got 0.015 molar. Okay, and from the solution of calcium sulfate, the calcium ion and sulfate ion concentrations are the same, and it contributes 0.010 molar. Okay, and the remaining 0.005 molar is contributed by calcium sulfate ion pair. Okay, so the calcium ions and sulfate ions, they are oppositely charged, so they are put together, still in solution, yeah, still in dissolved state, they behave. Okay, so this is we call ion pair. All right, so it contributes 0.005 molar, right? So total solubility is 0.015 molar. Well, here is the observation. When inert, this potassium nitrate, the salt is added to the saturated solution of calcium sulfate, okay, more solid of calcium sulfate dissolved by about 30%. Okay, here you add potassium nitrate and then this case p value, although it's the same, this solubility, okay, of calcium sulfate increases. Okay, here the inert means do not react each other. Okay, potassium ion or nitrate ion don't react with this one, calcium ion or sulfate ion. Okay? In general, adding inert salt makes solubility increase. Okay, and why? Why? What makes the solubility increase? Okay, so we have to answer that question. Okay. Here is the explanation by ionic atmosphere. Okay, let's consider. Okay, in this case, calcium and sulfate ion case. As we have already seen in the first few slides, okay, the round cation, yeah, there are water molecules. Okay, so round also anion, there are water molecules. But in this case, so since you added potassium and nitrate ions round this calcium ion, this one, nitrate ions now distribute. Okay, they um, surround this calcium ion. Likewise, around the sulfate ion, there are, we don't know how many, there are potassium ions. Okay, and what is the result? So this nitrate ion, since it takes the negative charge, okay, so it contributes. This one ionic atmosphere, we call it ionic atmosphere. It contributes partial negative charge to this calcium ion. So as a result, yeah, the effective charge of calcium ion is not divalent, but it is smaller than +2. Okay, because of this one. Yeah, the partial negative charge, okay, contributed by this nitrate ion. Okay, and by the same argument, this effective charge of sulfate ion is not -2, is smaller than -2 because the partial positive charge contribution from potassium ion. Okay, so effective charge is 2, not -2, -2 plus delta. Okay, so actual electrostatic attraction between calcium ions and sulfate ions becomes weakened. All right. So here, a spherical cloud of charge surrounding ions in solution. The charge of ionic atmosphere, okay, is smaller than charge of central ion. Okay, but this one, delta minus this partial negative charge cannot be greater than this central ion charge, which is +2. Okay, this delta minus, maybe we don't know, maybe minus 0.5 or minus zero point 0.7 or minus 1.0, or but never greater than +2. Okay, like right here. So delta plus, yeah, this one cannot be greater than -2. Okay, anyway, the effect of adding inert salt is to weaken the charges of central ion. Okay, yeah. So increasing ionic strength, you add um, these ions, that means you increase the ionic strength, reduces the attraction between anions and cations. Okay, which makes larger solubility. Okay, yeah, this one. So this one, since the charge is reduced, there will be more dissolution. Okay, because the attraction between these two ions are weakened. Okay, yeah, here is a demonstration, and which is the someone studied the solubility of potassium hydrogen tartarate. Okay, this is potassium hydrogen tartarate, and someone studied the effect of added salt. Uh, he added these four species: magnesium sulfate, sodium chloride, glucose, and potassium chloride. Okay, and then uh, he studied the the solubility of this one, this potassium hydrogen tartarate. Okay, and this one, when he added potassium chloride, the solubility of this species becomes smaller and smaller as the concentration of added salt increases. Why? Because this is the um, common ion effect. Yeah? These potassium ions are common here. Okay, if you add potassium chloride and this potassium ions concentration gets higher, so by the Lewis-Chatelet principle, the equilibrium shift toward this the left side. Okay, to make the equilibrium constant. All right, but when you add glucose, as you know, glucose doesn't have any charge. It's a neutral, so it doesn't have any effect on the solubility of potassium hydrogen tartarate, right? Okay, so the solubility never changes. Okay, it's around 0.03 molar. All right, but when you add sodium chloride or magnesium sulfate, the solubility increases. Okay, as you add more and more these salts. Okay, but here you have to pay attention to the fact that the magnesium sulfate effect is what more than the sodium chloride. Okay, the the, the reason is the same because this magnesium uh, ions and sulfate ions are surrounding the uh, the tartrate ions and also these sulfate ions. Okay, likewise, sodium ions now surrounding this tartrate ion and chloride ion surround the potassium ion. Okay, so as a result, solubility increases. For increasing rate is much uh, more rapid for magnesium sulfate than sodium chloride. Why? The only difference is that magnesium takes plus 2 charge, but sodium only plus 1. Sulfate ions takes minus 2, okay? But chloride ion takes only minus 1. So from this figure, you may say that the highly charged species have more, much stronger effect on solubility, okay?